We continue our syllabus today related to RF filter design. So here we focus on the insertion loss method. Okay, where insertion loss method partner with image parameter method. We have discussed in the previous sections where image parameter method has constant K, M derived filter section, and composite filter. Today we will go through to the insertion loss method, which is using either Butterworth and Chebyshev. So we will discuss in details related to this insertion loss method, which is basically suitable for high frequency application. Okay. As an introduction, okay, a filter is a two-port network used to control the frequency response at certain point in an RF microwave system by providing transmission at frequency within the pass band of the filter and attenuate in the stop band. That means we allow a signal to pass through, especially on the pass band, and eliminates at the stop band. So we have low pass, high pass, band pass, and band reject characteristic for this kind of filters. Insertion loss method actually using the network synthesized technique to design filter with a completely specified frequency response. So we design using the insertion loss method, basically using the we can say prototype low pass filter or normalized prototype of low pass filter, especially in terms of impedance and frequency. And then we can transform it to the real value with the impedance, real value with the frequency, or maybe to change from low pass filter to band pass filter, band stop filter, and so on. So basically, when designing a filter, okay, when designing a filter, so this is a frequency response, for example, for the low pass filter, a perfect low pass filter. So basically, we want to have a insertion loss of 0 in the pass band and infinite attenuation in the stop band. So this is the ideal case of the low pass filter or the filter. Unfortunately, in real world, we cannot get this. We cannot get this kind of filter. So what we want is to have a design of a filter that's near to this characteristic. So we want that the filters that have a sharp cutoff frequency and the attenuation is maintained at a certain level. If this is 30 dB, so this is the attenuation continues that within the minus 30 dB, for example. So we have seen the image parameter method on the previous videos, which is usable for some application, especially in the low frequency. But we want to improve more. That's why we introduced this insertion loss method. For example, okay, we want to design a desired response. If we want to have a minimum insertion loss, it's important to have a Chebyshev response, a binomial response or Chebyshev response. If we want to have another one, which is maximally flat, then we can have that maximum sharp cutoff frequency using the maximally flat technique. So we have two, Chebyshev and maximally flat technique. So before we go any further on the maybe calculation or derivation, so we look back to the basic of the insertion loss method. So basically, we look on the these two-port networks. Okay, we look of this concept. In this technique, the relative power loss due to a lossless filter with reflection of gamma in terms of frequency is specified in the power loss ratio, which is defined in this formula, which is power loss ratio, PLR, is equivalent to P incident over P load. And we have this equation. And finally, we have PLR is equivalent to 1 minus gamma omega to the power of 2 to the power of minus 1. If we are looking for the, okay, so if we're looking at the spot, the load and the source port, which is matched, then we have a power loss ratio of S to 1 to the power of 2. So in the book, in the microwave engineering book, you can see the details of the derivation. So here is some part of it. So if we look at section 4.1 in the book, we know that gamma omega to the power of 2 is equivalent to m over m plus n. And if we include this m and n in the polynomial, and we can get this PLR 1 minus 1 plus m over n. So now, from that PLR, power loss ratio, now we analyze it using the low pass filter for maximally flat. Maximally flat, also known as Butterworth types of filter, where are using the power loss ratio equivalent to 1 plus k to the power of 2 omega over omega c to the power of 2n, where n is the filter order and omega c is the cutoff frequency. If k is equivalent to 1 and PLR, we will have a PLR equivalent to 2 at omega equivalent to omega c. So that means m omega divided by omega c, we have 1. 1 to the power of 2 is 1. So PLR is equivalent to 2. So this is the power loss ratio versus frequency, the frequency response of the low pass filter, maximally flat or Butterworth. Okay, so maximally flat with 1 is the pass band and attenuation at the stop band. So this is the equation for basic power loss ratio, and this is with a k equivalent to 1 and omega equivalent to omega c. For the case of W is large, then we can have a power loss ratio of this equation. And from this, we learn that the insertion loss is basically 10 log to the PLR, not 20 yet. Okay, so insertion loss is 10 log power loss ratio, where it increased by 20 n dB per decade. So for each decade, it will increase with 20 n. If n equivalent to 1, so there's 20 dB per decade. If n is equal to 2, so you just multiply it. For the stop band, for the maximally flat low pass filter. Next, we move to the equal ripple, or it is called the Chebyshev filter. Chebyshev type of filter using this polynomial Tn. Okay, polynomial of Tn. Previously, we used m and n for the maximally flat or butterworth. So this is the equation of the equal ripple power loss ratio equivalent to 1 plus k to the power of 2 to Tn to the power of 2 and omega divided by omega c. So the frequency response, so here we have the ripple here where the 0.531 dB, so you can use it, okay, where the amplitude is 1 and 1 plus over 1 plus k to the power of 2. So normally, the number of order is chosen to be an odd or integer when the source and load impedance are equal. Okay, when source and the load are equal, so we choose n equivalent to 1, 3, 5, 7, and so on. For large omega over omega c, so we have the power loss ratio of this equation, and from here we learn that for butterworth, with the butterworth filter, an increase of 20 n dB per decade for butterworth, but with the extra factor 2 to the power of 2 n over 4. So that means there is more roll off for the Chebyshev type of filter. So here, for example, n equivalent to 3, we have a 12 dB per decade. N equivalent to 5, we have the 24.1 dB per decade. So slightly adjustable with the butterworth filter. So here the comparison of the equal ripple and maximally flat. So equal ripple, of course, the difference is it has a ripple. Okay, whether 0.513 dB, so it has ripple. So it has problem with ripple. However, it has a, what we can say, a sharp cutoff frequency compared to the maximally flat. The maximally flat has a good, what can say, the passband amplitude. However, the cutoff frequency is slightly is less sharper compared to the equal ripple. So there is a trade-off between the whether you want to choose equal ripple or maximally flat in your design. If you want to have a sharp cutoff frequency, okay, then you can use the Chebyshev or equal ripple. But if we want to have a minimum insertion loss, okay, you can use the maximally flat type of filter. Besides these two filters, which is Chebyshev and Butterworth filter, we have the elliptical filter. So elliptical filter has a equal ripple, okay, respond in both pass band and stop band. So it has a ripple on the pass band and stop band. And another type of filter is called the linear phase filter. Important that there be no signal distortion and the phase of the filter must be linear in the passband. So the keyword here is the focusing on the phase of the filter for the linear phase filter. Okay. We continue our course for the design of the filter design. Generally, the procedure for designing this filter can be summarized in 3 steps. The first one is the filter specification, which this includes the cutoff frequency, the stop band attenuation, the pass band insertion loss, the pass band behavior, and etc. Second is the design of low-pass prototype circuit. In such a prototype, for example, R equivalent to 1 ohm and omega C equivalent to 1 radian per second. So this basically a normalized value is included or normalized prototype circuit. Third, we can scale and conversion and make a conversion. So this which include the frequency scaling and impedance scaling. So because of what? Because of previously we are using the impedance equivalent to 1 and omega C equivalent to 1 for a normalized prototype circuit. Here, okay, we multiply back with the real value of impedance and the real value of frequency. In the same time, okay, if we want to design to the not only low pass filter, we need to do conversion to the whether high pass filter, band pass filter, and band stop filter. So we need to do the conversion. Okay, so this video is just for the part for the basic introduction on the filter design. We continue with the next part of the video.